By the time most investors encounter green hydrogen, the conversation is already framed the wrong way. The focus is usually on technology, electrolyzer efficiency, capital cost curves, future breakthroughs, or how quickly learning rates might drive prices down. That framing leads to a natural follow-up question. When will green hydrogen finally become competitive everywhere? At industrial ports, that question is irrelevant. Green hydrogen does not succeed at ports because it is cheaper, cleaner, or more advanced. It succeeds because the systems there are already under stress. And that stress is not a temporary condition, it is structural. Understanding this distinction is critical for investors. Hydrogen does not create value in relaxed systems. It creates value where existing systems are constrained, overloaded, expensive to reinforce, or commercially exposed. Ports concentrate these conditions more reliably than almost any other location in the energy system. The first form of stress that matters is grid stress. Ports are where offshore wind and coastal renewable generation physically land. Subsea cables come ashore at ports because that is where heavy infrastructure, substations, and industrial demand already exist. As renewable penetration increases, these landing points feel the strain first. Power arrives in large volumes, often faster than it can be transmitted inland. Congestion becomes routine. Curtailment becomes normalized. Electricity prices swing sharply, sometimes collapsing entirely. From a grid planning perspective, this is a problem. Reinforcing transmission is capital-intensive, slow, and politically difficult. New lines require years of permitting and billions in investment. During that time, congestion persists. From an investor perspective, this stress is not a flaw. It is the source of value creation. Green hydrogen absorbs electricity precisely at the point where the grid cannot. It converts excess electrons into molecules without requiring immediate reinforcement of the transmission network. That conversion only has value when the grid is constrained. In unconstrained systems, electricity simply flows elsewhere and hydrogen becomes redundant. This is why hydrogen economics fail in regions with abundant, unconstrained power. Cheap electricity alone is not enough. What matters is electricity that cannot be moved easily. Ports provide that condition by default. The second form of stress is utilization pressure. Industrial ports host processes that cannot afford to stop. Refineries, chemical plants, fertilizer facilities, and terminals operate continuously because downtime costs millions. These industries already rely on hydrogen as a core input. Any disruption threatens throughput, safety, and margins. This creates a discipline that hydrogen projects elsewhere rarely experience. At ports, hydrogen cannot be intermittent. Electrolyzers are not sized for pilots or demonstrations. They are sized to serve real continuous demand. Utilization is not an aspiration. It is enforced by the surrounding system. For investors, this matters more than almost any technical parameter. Hydrogen economics are brutally sensitive to utilization. Capital costs dominate. An electrolyzer that runs only part of the year produces expensive hydrogen, regardless of how efficient the stack is. An electrolyzer that runs most hours of the year behaves more like infrastructure. Ports force hydrogen into that infrastructure behavior. They eliminate the option of running when convenient. The industrial processes downstream demand continuity. That requirement stabilizes utilization and spreads capital cost across far more kilograms of hydrogen. The third stress is land and infrastructure scarcity. Ports are dense environments. Space is contested. Every square meter competes with cargo handling, storage, logistics, and throughput. Adding new infrastructure is expensive and politically sensitive. This scarcity changes how solutions are evaluated. In relaxed environments, planners can propose new transmission lines, new substations, or new terminals. In ports, those options are slow, disruptive, and often resisted. Green hydrogen gains value here not because it is elegant, but because it is compact relative to alternatives. An electrolyzer installed inside an existing industrial footprint can absorb large amounts of power without requiring immediate external expansion. It internalizes congestion relief. In stressed environments, solutions that minimize new interfaces win. The fourth stress is transport economics. Hydrogen is uniquely sensitive to distance. Compressing it consumes energy. Liquefying it consumes even more. Trucking it adds operating cost, safety complexity, and emissions. Long pipelines require capital, permitting, and time. In many hydrogen projects, transport quietly destroys the economics before the molecule reaches the user. This is one of the most common reasons inland hydrogen projects struggle. Ports invert this dynamic. Hydrogen production and consumption occur within the same industrial zone. Pipelines are short. Pressures are controlled. Safety systems already exist. By keeping hydrogen inside the fence, ports delete entire layers of system cost. This is not a marginal improvement. For investors, it removes multiple sources of uncertainty simultaneously. Shorter transport distances reduce CapEx, OpEx, permitting risk, and execution risk. Hydrogen becomes easier to underwrite not because it is cheaper everywhere, but because the system is simpler. The fifth stress is carbon exposure. Ports concentrate some of the most carbon-intensive and export-exposed industries in the global economy. Refining, chemicals, and fertilizers face increasing pressure from carbon pricing, border adjustment mechanisms, and buyer requirements. This pressure is commercial, not ideological. It affects contracts, access to markets, and financing conditions. Green hydrogen relieves that pressure by removing carbon at the point of production. This turns hydrogen into a defensive investment rather than a growth experiment. Defensive investments behave differently in capital markets. They are approved to protect existing cash flows, not to chase uncertain upside. Boards approve defensive infrastructure more readily than speculative technology. Lenders view it more favorably. This is one reason port hydrogen projects often advance toward execution, while other projects stall despite generous incentives. The sixth stress is regulatory and safety alignment. Ports already operate under strict hazardous materials regimes. Emergency response systems, zoning frameworks, and liability structures are designed for flammable gases, high pressures, and continuous industrial operation. Hydrogen does not introduce a new category of risk in this environment. It adds complexity, but it fits within existing institutional capacity. This matters because hydrogen fails fastest in environments that are not equipped to manage it. In relaxed systems, hydrogen adds fragility. In stressed systems that already manage pressure, hydrogen integrates. When these stresses are viewed together, a pattern emerges. Green hydrogen does not work because it is green. It works because it relieves pressure inside systems that are already under strain. This also explains a common failure mode. Developers often attempt to replicate port hydrogen projects inland by copying the technology while ignoring the system context. They install electrolyzers where electricity is abundant and unconstrained, where demand is optional, where transport distances are long, and where carbon pressure is weak. The result is underutilized assets and stranded capital. Investors should recognize this pattern early. Hydrogen is not a uniform market. It is a stress-dependent opportunity. Where stress exists, hydrogen behaves like infrastructure. Where stress is absent, hydrogen behaves like a subsidy-dependent experiment. Ports sit at the extreme end of the stress spectrum. They concentrate grid congestion, industrial continuity requirements, land scarcity, transport constraints, carbon exposure, and regulatory complexity. That concentration is not accidental, it is structural. This is why green hydrogen economics stabilize at ports before they stabilize anywhere else. It is also why ports act as filters. They reveal which hydrogen concepts survive contact with reality and which ones do not. For investors, the implication is not optimism, it is selectivity. The question is not whether green hydrogen will work in general. The question is where stress already exists and whether hydrogen meaningfully relieves it. When investors learn to underwrite stress instead of technology, the field narrows dramatically. Announcements fade. Pilot projects lose relevance. What remains are projects embedded in systems that cannot function efficiently without relief. That is why capital flows to ports. Not because they are visionary, but because they are constrained. Not because hydrogen is exciting, but because pressure demands solutions. Green hydrogen is not an energy transition story at ports. It is a system stabilization story. And for investors, that distinction makes all the difference. If you are evaluating green hydrogen opportunities and want to understand where system stress turns hydrogen into a bankable infrastructure asset rather than a speculative narrative, this is exactly the type of analysis developed inside H2 Hub by Renewable Energy. It exists for investors and advisors who need to separate projects that relieve real constraints from those that only look good on slides.